Welcome to qnawire.
Okay, so in this case, you have a rocket that's going up and it is also ejecting some mass here at a certain rate. And you want to derive equations for the velocity, the acceleration, and then finally the position, compare them to what you were given. So you were given that the velocity of the exhaust is around 1500 meters per second. And the change in mass with time, so dmt here is about 2.5. And then you're told that the time that it takes to lose all the mass here, which is tb, is around 132 seconds. So the first thing you want to do is find an expression for the velocity. So that expression has already been derived, and that's equation 9.43 in the chapter. And that equation says V final minus V initial is equal to the velocity of the exhaust times the natural log of mi over mf. So already you can see that we have an expression that looks similar to what was already given in the problem. So now what you have to do now is substitute some of the values that we had that were given so that we can make this look like the answer. So they tell us that this is equal to the rate k over here. And they tell us that this thing starts from rest, so vi is equal to 0. So that means that this term goes to 0, which means the final velocity is actually equal to ve natural log. So notice the initial mass is given, and the initial mass is actually in the solution that we want. So we actually want to remove the final mass in here. But we know that if it's changing at this rate, then the mass at any point in time is going to be the initial mass minus the total mass that we have lost here, which is the rate of change of mass times time. So this is just going to be kt. And that gives you an expression for the velocity. But to put it in the form that's given, you have to reverse this log here. So that's just a matter of putting a negative sign here. So that becomes negative VE natural log of MI minus KT over MI. So now if you flip this, then you have to carry a negative sign out here because it's log mi minus the denominator. So if we change the positions of these, you have to take on a negative sign on the outside. So notice that this can be simplified further. So that's negative e natural log of this is 1 minus kt over mi. And that's your velocity there. And then they ask you to plot what that velocity would look like. So essentially now what you want to do is put in the numbers that you were given. In this case, I think the last thing that they give you is that the initial mass was 360 kilograms. So in this case, you look at this equation, you substitute all the values that you were given. So you know K, you know Mi, and you know VE. So you're going to have an expression that looks something like 1500 natural log of 1 minus 2.5 over 360 times t. So we know, so you can use your favorite plotting program or just get a bunch of points and plot them, and you'll see that from 0 to around 132 seconds, which is the time window that you're given. So when the time is 0 here, notice that this is the log of 1, which is 0. So this has 1 point up here, and for very large values of time, So if this term is really, really large here, notice that this is 1 minus, so it becomes, so actually, if you look at when this is equal to 1, so when 2.5 t is equal to 360, that natural log is actually natural log of 0. And natural log of 0 blows up. So this thing is actually just going to go up like this. And you can put in the numbers and find the points if you want, but the graph should look something like this. And then, so now for part B, you have to come up with an expression for the acceleration. So we know that the acceleration is always going to be the derivative of the velocity with respect to time. So in this case, we take our expression here, which was negative VE natural log of 1 minus KT over M I in this case. And then we want to take the derivative of that. So that is going to be, so this is a constant, which stays as it is. But before you do so, notice if you, for a natural log, you take a derivative, this is like a chain rule here. So the derivative of the inside is just going to be K over Mi, but there's a negative sign here, there's a negative sign here, so that takes away that negative sign. So you just have something like that. But now when you do a derivative of the natural log, this is going to be 1 over whatever is inside that natural log. So that's your expression for the acceleration, but that can be simplified further into something that looks like KVE over, you multiply this mass in here, you get Mi minus KT. And that's your acceleration expression, which matches what's given in the solution. And again, you have to plot that from maybe 0 to 132 or something here. So again, you do the same tests when t is 0. So when this t is 0, notice that this is some non-zero value here, because the acceleration it's not going to start exactly at 0, because when t is 0, this expression starts 0. So that will start somewhere, let's say over here. But then as t increases, this denominator gets smaller, so it means this whole value goes up. So this can actually look like something like this, but it's not exactly a log, but it's just going to increase. So then for part C, this thing is asking you now to find an expression for the position of this thing. If you want to graph the position, again, you have to derive an expression for the position. But we know that the position x final minus x initial, whatever it is you want to put here, is going to be the integral of the velocity with respect to the integral of the velocity with respect to time. So this will give you the position or the change in position, because we know that the velocity is a derivative of the position. So to go backwards, you have to integrate the expression. So we already have an expression for the velocity. So we want to integrate that expression. So this is going to be the integral from 0 to t of negative VE natural log of 1 minus KT over MI in this case. So you can actually look up the integral in the table, and the one that you want to use here is something that looks like this. Natural log of x plus b. Here, this integrates into x plus b over a. So you can look up this integral here. There's no need to redo it if it's already given somewhere. So that's ax plus b minus x here. So this expression looks exactly like the expression that you have. So you just substitute a with negative kt over m and b with 1, and then you see that the final expression that you get will look something like, so this would be VE multiplying everything inside bracket, and that would be mi over k minus t. This is multiplied by the natural log of 1 minus kt over mi plus t. So notice here, b is actually k over m, but this is so once you evaluate it, no, a is k over m. So 1 over a is m over k. So that's why this is written this way. And because the negative sign that you had before changes the sign here, and it changes the sign here into something like that. So this is your final expression for velocity for the position, which matches what you are given as well. And you can notice that when t is 0, this is 0, this is 0. So when t is 0, everything is 0. So you don't have a proportionality constant there. So then now you just want to plot this thing. And I'm just going to sketch it. So you have 0 to 132 again. And notice again that, so when t is 0, this thing is at 0, like we said before. And then this thing just increases by it. So again, it increases in the same manner, but this dominates. This natural log function dominates. So you will see something that looks like a natural log going up, and that will be your. So this would be your position versus time graph for that problem.